geospatial information system, and applications of AI and ML in civil engineering.
Yes, sir, we can start now.
Yeah, right. Good afternoon, all. I'm Dr. Hemaraju Pollayi from GITAM University, Hyderabad. Thank you, Professor, for organizing WINS. I'm going to present on the topic stealth carbon nanotubes, artificial intelligence, machine learning based modeling of nano-structured composites for attenuation and shielding in the aircraft. Stealth technology, also called low observable technology, is any military technology intended to make the vehicle or missile nearly invisible to the enemy radar or any other electronic detection. So the goal of stealth technology here is to make the
Raju,
aircraft
can you make
invisible.
it full screen? Can you make the PowerPoint presentation full screen?
Sir, it is in full screen only right now.
Please make it slideshow mode. Yeah.
So now is it visible?
No. Share your screen.
Yeah, sure. So now is it visible?
Yes, it is visible. Yeah.
Is
Can you
it
click
now it
on the
is?
slideshow there at the bottom?
It is showing, sir. Here it is slideshow only.
Just click, but it's not showing up here. That's okay. Maybe you can click on home so that it becomes bigger. On the top, next to file, you can click on home, and you can also close the sidebar.
Just.
You can go to view and hide sidebar, and also click on home.
Sir, now is it visible?
Yeah, it's visible. Please go ahead.
Sir, is it a full screen or not?
No, it's not full screen, but it's okay. We can manage.
Yeah, maybe.
Don't worry, Raju. Please go ahead.
Okay. Yeah. Yeah. Good afternoon, all. I'm Dr. Hemaraju Pollayi from GITAM University, Hyderabad. Thank you, Professor, for organizing international WINS. I'm going to present on stealth carbon nanotubes, artificial intelligence, machine learning based modeling of nano-structured composites for attenuation and shielding in the aircraft. The stealth technology, also called the low observable technology, is any military technology intended to make the vehicle or missiles nearly invisible or any other electronic detection system. Here, the goal of the stealth technology is to make the aircraft invisible to the radar. There are two ways to create the invisibility here. One thing is we can change the composition of the material and we can change the shape of the aircraft. Left hand side, you see the conventional aircraft with normal design with a rounded shape. Right hand side, you see the stealth aircraft with stealth design with flat surfaces and sharp edges. The design of stealth requires integration of many techniques and materials. There are different types of stealth technologies. There are 4 types, in fact: visual stealth, infrared stealth, acoustic stealth, and radar stealth also. So I'm working on radar absorbing materials. In short, we call it as a RAM, and the radar absorbing structures as well, RAS. These RAMs are used for the absorption of electromagnetic waves. So here, in case of a radar absorbing materials, so right now I am focusing on the carbon nanotubes. Carbon nanotubes are the tubes made of the carbon. So they have the unique nanostructure properties. These carbon nanotubes are very useful in the aerospace applications due to the superior electrical, mechanical, and thermal properties. So this is the terminology we use throughout the presentation. Can you see the slide number 2?
No, we are still on slide number 1.
Slide number 2 is visible here. Now, sir, now?
No, it's still the title slide.
Title slide only. Yeah, just.
Now we can see it. Yeah. Go ahead.
Sorry, is it visible now? Full screen?
Yes. No, full screen is still not there, but I think it's okay.
Yeah, so this is a terminology we use throughout the presentation. Artificial intelligence, we know, is a simulation of human intelligence processed by machines, generally the computer systems. Machine learning is a type of artificial intelligence that allows software applications to become more accurate at predicting outcomes without being explicitly programmed. Carbon nanotube, throughout the presentation, we call it as a CNT, is a tube made of carbon with diameters typically measured in nanometers, 10⁻⁹ meters. So generally the nanoscale ranging from 1 nanometer to 100 nanometers. So by definition, the stealth aircraft is effectively immune to the radar, radio detection and ranging at normal combat ranges. So here you can see there are 3 artificial intelligence, machine learning, deep learning, which are subset of the artificial intelligence. Here we can use the carbon nanotube to make the aircraft stealth. So the motivation for the, sir, can you see the motivation slide?
Not yet. Yeah.
Sir, can you see the motivation slide now?
Yes, Raju.
Okay, so there is some problem, I think. Yeah. So this is the motivation for my present work. The question arises, can I use carbon nanotubes in the attenuation and shielding from the radio waves for the next generation stealth aircraft? The answer is yes, because the CNTs have unique nanostructures that display desirable properties of any other known material. So here we can see in the figure, I cited the source as well. There is a aircraft which is flying. If you send the signals or electromagnetic waves from the radar system, it will reflect back to the antenna. But if you cover the aircraft, or if you cover the full aircraft with the carbon nanotubes, we can see only the signals are going out from the radar, radio detection and ranging, but it is not reflecting back. So it implies the carbon nanotube is absorbing all the electromagnetic waves. So the next question arises, is there any other alternative for the carbon nanotubes? Yes. So there is another material called boron nitride nanotube. So if you suitably engineer the boron nitride nanotube, so it is the alternative to the carbon nanotube. This slide shows the modeling and applications of carbon nanotubes. Please confirm whether the slide.
No, sir. Slide is not visible actually. You come out of the slideshow mode. Generally, you present. I guess that will work.
Okay.
Yeah, like
Yeah,
this.
now.
Yeah, now it
Okay,
is.
fine. Okay, yeah. So maybe there is some problem. Yeah, fine. This slide shows the modeling and applications of the stealth carbon nanotubes. Here you can see there is a aircraft flying. We can change the material, we can change the shape as well, and we can change the size of the surfaces as well. So when we are sending the electromagnetic waves from the antenna, So we can play with the polarization and wavelength of the waves to make the aircraft stealth. So in order to do that, we have to understand the properties of the CNT. So this is the graphene sheet, and we can rotate the graphene sheet and we can form it as a single-walled carbon nanotube and a double-walled carbon nanotube and multi-walled carbon nanotube as well. This figure shows the molecular bonds and the carbon atoms in the graphene sheet. So if you want to model mathematically, the single-walled carbon nanotube modeled as a thin cylindrical shell. So in order to do that, we have to play with the chirality, which is the XY coordinate of each carbon atom. So this slide shows the weight and density of the carbon nanotubes. Weight and density of the carbon nanotube both are function of inner diameter, outer diameter, and a number of walls as well. So here I am making some assumptions. The distance between the two carbon atoms is around 0.1421 nanometer, and the distance between the two walls is about 0.34 nanometer, and I neglected the contribution of the electron density to the outer diameter, and the aspect ratio should be more than 1000. So this is the equation. There are many equations behind this. This is the density of the multi-walled carbon nanotube. This multi-walled carbon nanotube coded in the Python, as well as there is a software called CNT bands. I modeled in the CNT bands also. In the latter part of my presentation, I will show you the Python code as well as the CNT bands. In the Python code, there are 4 inputs. One is chiral indices with the 2 integers, and bond length in angstrom units and number of unit cells. The output is either you can have XYZ format or lamps. Whereas in the case of CNT bands, the chirality, also known as N and M, tight binding energy in electron volts, the carbon-carbon spacing in angstroms, and length in the 3D view. So these are the inputs for the CNT bands. So coming to the attenuation and shielding in the aircraft, the electromagnetic wave collides surface of the carbon nanomaterial nanotube, in fact, can be transmitted, reflected, and absorbed. The ability of the shielding material to reduce the electromagnetic waves can be defined by the electromagnetic interference shielding effectiveness, and it is the sum of the reflection, absorption, and multiple internal reflections of the complete mechanism. So here you can see on the right hand side, there is an incident. If you coat the whole aircraft with single layer, the shielding material, in our case it is a carbon nanotube, some part of the wave will reflect back and some part will transmitted. And similarly, if you have different layers, for example, if you use multi-layer carbon nanotube, so the absorption capacity of the material is more. So this slide shows the attenuation coefficient depends on the thickness of the diamagnetic material, and the magnetic permeability of the material can be defined by eta. So this is the equation we use for the attenuation coefficient. Here mu r is the relative permeability, and A is the inner radius, B is the outer radius of the carbon nanotube. So if you don't want shielding, implies eta equal to 1 for mu r equal to 1. If you substitute mu r equal to infinity, then there is a perfect shielding on the surface of the aircraft. Here, in our case, the shielding performance is expressed in terms of the decibels. The value expresses degree to which the electromagnetic wave is attenuated. The shielding performance can be defined by this equation, 20 into log of intensity of the electric field after shielding by the intensity of the electric field before the shielding. So these are the outputs from the computational modeling of the carbon nanotube, which is implemented in the Python framework. So to start working on the carbon nanotube, I have collected a data set from University of California, Irvine machine learning repository. So these are the coordinates of the carbon nanotube. Carbon nanotube with the initial coordinates, and these are the final coordinates, and these are the this graph, the bar chart shows the chiral NDS N and M. So these are bottom you see the calculated atomic coordinates of the carbon nanotube. So here in our case, I implemented using artificial neural network here. So in this case, I will show you the image as well. I have used min-max scalar and ReLU activation function and the softmax as well for the activation. Here, 70% data is for the training and 30% of the data is used for the testing. So this slide shows the simulation of carbon nanotubes using the CNT bands. CNT bands version 2.7.3 is used to simulate the electron band structure and the density of the states. The conductivity of the armchair structured carbon nanotubes appears to be the superior to the other metallic carbon nanotubes. Literature says that armchair, meaning the M equal to N values are good for the aircraft. So other than armchair, we have the jig-jog and chiral as well. So these are the outputs, simulation outputs from the CNT bands, which clearly shows the band structure of the carbon nanotube. Unsupervised learning applied to the molecular dynamics, and these two figures shows the variation of carbon nanotube diameter with respect to the number of points in the data set. So this slide shows the variation of radius in 11 data sets and variation of the density in the 11 data sets and optimization of the cluster. Here the number of clusters equal to 6 here. This slide shows the visualization of the clustering. We can see all diameters are clustered at a particular location, and let us say red in color. So about 0.5 meter, the density is more here. And similarly, in this graph, radius versus density, all the radius of the carbon nanotubes are clustered. So the clustering is very important to calculate the optimum diameter of the carbon nanotube. So these are the conclusions. The present work described a methodology for modeling the stealth carbon nanotubes in attenuation and shielding from the radio waves for the next generation aircraft within the artificial intelligence and machine learning based framework using the Python. The main contributions of the paper are I have selected and developed 11 datasets for the carbon nanotube of diameter ranging from 0.81 nanometer to 4 nanometer, and determined the weight and density of the carbon nanotubes for the attenuation and shielding of the stealth aircraft, and the optimized diameter of the carbon nanotubes using the k-means clustering algorithm, developed artificial neural network models for the CNT prediction and scaled the futures using the min-max scalar with 70% of the dataset for the training and 30% dataset into the testing. And I have compared the performance of the RMS Prof optimizer with the ADAM optimizer and observed that the ADAM optimizer performed better for the present model. So these are the results from the artificial neural network. The training loss with the RMS Prof is 0.00011. Right? If you observe the other value, it is about 8.53 into 10⁻⁵. Then the test loss with RMS Prof is about 0.00013, but whereas the test loss with the atom is about 7.7 into 10 power minus 5. Still, there are problems. We can always manipulate the molecules in the CNT chemically and physically for the stealth aircraft. So we can play with the chemical properties and physical properties of the carbon nanotubes. We can take the advantage of the carbon nanotubes that have amazing and unique electronic, physical, chemical, and mechanical properties, which lead to the incredible forms of strength and conductivity. And I have implemented the carbon nanotubes for the attenuation and shielding in the Python. In future, if you want to completely work on the stealth technology, the design for the stealth requires the integration of four major types: visual stealth, infrared stealth, acoustic stealth, and radar stealth as well. This slide shows the Python framework. So in the first so this is a Jupyter notebook. So in the advantage of Jupyter notebook is we can run the cell-wise or compartment-wise block. So in the first, you see there are different libraries that are existing in the Python. I'm using some of those, such as NumPy, Pandas, Matplot library, Scale, and K-means. So first we have to create a data set, which is a CSV, which is in a CSV comma separated value format. Then load the data set and check again with the list whether all values are reading properly or not. And with the optimum number of clusters, use the K-means algorithm. K-means is the existing library in the Python. Then finally, do all the clustering for the complete 11 sets. This slide shows again loading the carbon nanotube comma separated value file. So here, this is actually, it shows the ANN part of the carbon nanotube. So if you observe very clearly here, so it will generate the atomic coordinates of the carbon nanotube. So we can use the min-max scalar in the Python library, and we can again split into the complete data set. We can split into training and testing data set. And here in the place of activation function, we can have different functions. So for example, you can replace softmax with the ReLU and other existing functions if you want to play with the activation function. And finally, this if you run this block, you will see the predicted and testing values that completes the problem. That's all from my side for today. Thank you for your attention. If you have any other questions, please ask. Hello, sir. Can you hear my?
Yes, can you hear me?
Yeah.
Well, thank you for the presentation. My chemistry is a bit forgotten already, but I do have a question. In one of the first slides, you show the carbon bonds. So every carbon atom is bonded to 3 carbons, right? And one of the bonds, exactly, one of the bonds is a double bond, while there are 2 single bonds. So
yes.
How does it affect to the performance of the nanotube, whether this double bond is in the axial direction of the tube or in the circumferential one? Or is it not possible to get both configurations?
Thank you very much for asking the question. So we can change the bonding positions here so that it can be very effective in absorbing the electromagnetic waves when you are using the graphene sheet for the stealth technology. You can always play with these bonding, and we can always play with the distance between these 2 carbon atoms as well for the effective stealth technology. So if you are not very happy with the carbon nanotubes, there is other option we have. We can play with the boron nitride nanotube as well. So is that answer to your question, sir?
Yes, thank you.
Sir, this is Fanindra. It is a nice
Yeah.
presentation. So have you evaluated the absorption capabilities of different diameters of CNT?
We are working on it, Fanindra. Before that, we have to finalize whether single-walled carbon nanotube is good, or multi-walled or double-walled carbon nanotube is good for the shielding.
Okay.
So we have the formulation ready. Only thing is the thickness matters a lot.
Yeah, yeah.
In the flying object. So we are working on it.
So have you considered the properties dependency on the frequency of operation, or you're considering the properties as static properties?
No, properties are dynamic. Here you have to play with the polarization and wavelength also, and the thickness of the carbon nanotube matters.
So
Whether
you are
well,
considering the dependency of frequency as well in the properties for the properties of CNT. Like in the CNT's properties in which you are taking for the calculation of shielding effectiveness, you're considering like at what frequency, what are the properties of the CNTs? Those things are taken care of.
Properties, yeah. You can always play with the physical and chemical properties. If I say physical properties, I mean the diameter, length of the carbon nanotube and the architecture also. Right? How do you orient? How do you orient the carbon nanotube? That plays a major role. If you want to play with the chemical properties, for example, you have to play with the bond length here. For example, the distance between the two carbon atoms. You have to play with that. So you can play both chemically and as well as the physical properties as well.
You're planning of inverse problem as well. Like if we want to have an absorption capacity, can you tell us what will be the diameter of CNTs we can use, or what will be the thickness of the material we can use? Are you planning to work on that?
So out of my work presented right now, I found the optimum diameter is 1 nanometer.
Okay, okay, okay.
It's
It's based on
it all depends on the properties. You are right. Yeah.
Thank you. Thank you.
Guruji, any questions from your side, sir?
I think there are no more questions, Raju. Thank you so much for agreeing the last minute. So it was really nice listening to you after a long time, and you're working in an entirely different area from what I knew of you. Thank you, Raju. We'll move over to Guru Prasad's talk now.
Yeah, right. Thank you, sir. Thank you.